Alright, this is part 2 of Tuesday night lecture for Mr. Fender. College Algebra, 5 to 6:15, Tuesday and Thursdays. We are picking up with function capsules. Now in your notes, I gave you a list of function capsules. There's 7 of them that you need to know the information that's contained inside these capsules. I've given you the page numbers for them. You need to pay attention to the domain of each of these functions, the range, what the graph looks like, and its descriptors. And by descriptors, I mean these pieces of information down here. It's constant over what domain. It's continuous over what domain. Remember, we're talking about how we describe functions. Okay, that's what we're starting with in this section. Is it continuous or not continuous? And is it increasing, decreasing, or constant? And over what domain does that occur at? Here's the domain for the constant function. Here is the range for your constant function. Okay, notice what it looks like on a graph, both the way we graph it by hand and on a graphing calculator. Also, look at the chart. No matter what x value you see in your table on a graphing calculator, all of your y1 values are the same. This is how you can determine that it is a constant function. But because this is not going to be available to you on your final exam, you need to understand this information, and what this graph looks like. Now, you may be provided one of these two on your final exam as a multiple choice option, or they may give one of these to you and ask you to describe the function as whether it's constant or one of the other function capsules that we're going to discuss. Or if it's continuous, they may ask you what the domain or range of this particular function is by providing you just a picture. Okay, but all of this information is contained in this little function capsule. You don't have to go anywhere else to find it. It's right here. Okay, and all the page numbers and all the other function capsules are listed on their separate page numbers. So here's your constant function. There's your identity function, okay? Or it's just a simple line, y is equal to x. No matter what number you put in for x, you're going to get the exact same answer for y. If you notice, all these numbers match all along here for both the x and the y values. Then you've got your squaring function. Okay, that makes what we call a parabola. Okay, and wherever this function changes from decreasing to increasing, or if they happen to flip this upside down, wherever it changes from increasing going upward here to decreasing down the other way, that point right there is called the vertex. Okay, that's a vocabulary word you may want to write in somewhere. Okay, you need to know that that's called a vertex. Oh, actually, that's on page 2 of your notes. I apologize for that. Right here. The graph of the squaring function is called a parabola. Sorry for the shadow. The light seems to be changing on me as the sun goes down. The place where the graph changes from increasing to decreasing or from decreasing to increasing is called the vertex. Okay, this is for the squaring function. Parabola, vertex. 2 vocabulary words that are very important for you to understand about this squaring function. Okay, once again, you need to know where it decreases at, where it increases at, and whether it's continuous or not. Alright. So, on this particular graph, okay, something interesting happens. Okay, and there's a word, this is where we get into what we call symmetry. Alright, so if you can fold the graph along the y-axis, remember, is the one that goes up and down. So if you can fold that over the y-axis this way, and both the left and right sides of the graph will sit on top of each other no matter which way you fold it, then that function is said to have symmetry with respect to the y-axis. If this is true, then there's something about the points that you will always know. If you have any point AB that you can identify on your graph, then another point you automatically know is on your graph is negative A, positive B. So if this AB that you can identify is at -1, +2, then that means the -1, well, negative makes positive, so +1, +2 is also going to be on the graph. If this point right here is at +3, -4, then that means the point -3, -4 is also on the graph. Notice only the A changes sign, the B stays the same. So you're only changing the sign of the X value, the Y value is not changing. And you can see that in the table right here. X is +1, Y is +1. If X changes to -1, so the A became -A, then guess what? The B, or the Y value, is still +1. That is not changing. Okay, so that's where the squaring function, y equals x squared. Okay, this is the first one that we see symmetry with. So you need to know that this is symmetric with respect to the y-axis. You can fold this over either way. Okay, and this part of the curve will sit on top of this part of the curve. Well, a squaring function has an exponent of 2. There's also something called a cubing function. Cubing, or cubed, just means it has an exponent of 3. Okay, so once again, here's another function capsule for another function you're responsible for knowing the information for. Domain, range, where it increases, where it decreases, whether it's continuous or not. Okay, and now we come up to a new vocabulary word. Okay, right here. This is called an inflection point. Okay, this happens when instead of going from increasing to decreasing or decreasing to increasing, it goes from opening downward, it changes to opening upwards. Or if it was flipped, you could open it upward here, and then it would change and open downward on this side. Okay, so if you have a change in which direction the graph opens up, this side right here is opening downward, this side right here is opening upward. That spot where it changes that direction is called an inflection point. Okay, and that's also covered in your notes right here. Okay, now we don't have a specific name for this graph like we do for the squaring function where we call it a parabola, but you still need to know what the graph looks like. Okay, and what that point is called in case they ask you in a question like, where is the inflection point for the following graph on your final exam or on the test for this unit. Okay, you need to be able to identify these things. So this is vocabulary you need to learn. Your next capsule is the square root function. Okay, notice that this only has really one section that goes this direction. Okay, please pay attention to, once again, the information that's contained. Okay, and how these intervals change for these particular functions. The reason why there is no negative values for x over here is because you cannot take the square root of a negative number and still be a real number. Okay, once you try to take the square root of a negative number, you get into the imaginary category of numbers, and we have not covered those yet. And those are very, very difficult, if to try to take the square root of. Okay, you cannot take the square root of the negative number. So, okay, you need to recognize what that looks like. And then just like the square root, and we have the squared function, we also have a cube root and a cubic function. Okay, this time the root is a 3. Okay, notice what it looks like. Instead of opening downward this way and upward this way, now it sort of opens sideways. You got one that comes down low, but it opens more to the left, and then you got another piece that opens above, and it's more to the right. Now this can be switched. Okay, you can have it down here and then up here. Okay, once again, one part opening to the left, the other part opening to the right. Okay, once again, make sure you pay attention to the domain and range of the function, where it increases, if it decreases at all, whether it's continuous or not, and what the intervals are for those descriptions. And this is the first function where we can have another type of symmetry. This is said to be symmetric with respect to the origin. The origin, remember, is the point on the graph at 0, 0 where the x and y axes meet. So for this particular one, if you folded it over the x-axis, up and down, and folded it over the right, or the y-axis, left to right, you have to do 2 folds, okay, in order to see symmetry with respect to the origin. Okay, take this, fold it over, and then I have to fold it down. And then this graph would sit on top of this part of the graph, and that proves that it is symmetric with respect to the origin. Now, I did say about square root functions that it's limited to the real numbers, which is from 0 to positive infinity. You can't have a negative number in the square root function. Please make sure you pay attention to the limited domain. Okay, the x values are limited to including 0, because you can take the square root of 0 to get 0. So there is a square bracket there. It is inclusive. And then it goes to positive infinity. But no negative numbers can be in the domain. But the cube root function does not have this restriction. Okay, you can take this as the cube root of a negative number. And the last function capsule that we're going to cover is the absolute value function. Okay, it looks like a V. It is not curved. It's like 2 parts of a line. Okay, please pay attention to its also domain range, whether it's increasing, decreasing, and on what intervals, and whether it's continuous or not. The absolute value function is what we call a piecewise function. And we actually will not cover, I thought we covered more piecewise functions in a different chapter or later in this chapter, but we actually do not cover any more real piecewise functions other than the absolute value one. Please scratch out the second both. I did not mean to put that there. And so, but the absolute value function is the only one that is a piecewise function. All right, stay tuned for part 3.